Okay, this is a video to supplement lab number 2, the Reynolds apparatus. In lab number 2, we reproduce the famous Reynolds experiment in fluid dynamics, looking at transition from laminar to turbulent flow. Okay, first let me refresh your memory. I talked about the Reynolds number in chapter 1. It's a dimensionless parameter now named after Osborne Reynolds, an Irish engineer and possibly one of the most famous engineers of all time, certainly in the field of fluid dynamics. For flow in a pipe, the Reynolds number is rho v bar d upon mu, where rho is the fluid density, v bar is the average velocity in the pipe, which I've shown over here, d is the inside diameter of the pipe, and mu is the dynamic viscosity of the fluid. And Reynolds famously showed in an experiment in 1883 that this dimensionless parameter determines the character of the flow in the pipe. Reynolds found that at low values of this dimensionless parameter, the flow was laminar, so smooth, steady streamlines with layers of fluid flowing smoothly over one another with no lateral mixing. But at higher values of this parameter, the flow became turbulent, characterized by unsteady vortices. In fluid dynamics, these vortices are sometimes called eddies, and these eddies cause lateral mixing of the flow and make the fluid harder to pump. So this is Reynolds' famous paper, and this is an etching taken from that paper showing his apparatus. His experiment used a tank of water, and he could watch the water flow inside a glass tube, and he injected colored dye at the inlet to the pipe so he could see the flow patterns. And he made simple hand sketches of what he saw. These are two sketches taken from his paper. At low Reynolds numbers, the injected dye stream was carried in a straight line with the flow, but at higher Reynolds numbers, the stream of dye was mixed by the vortices that formed inside the pipe. Here's the modern apparatus that you'll use in lab 2. Again, there's a tank of water and a dye injection system at the tube entrance, and the water flows through a glass tube so you can see the flow. And here's the viewing area. I'm going to show you a short video of what happens to the dye stream as the flow velocity increases. In this video, the water velocity starts out low and slowly increases. At first, the dye is being carried directly downstream in a straight line by the laminar flow. But as the average velocity increases, you can see some waviness start to form. And as the velocity increases even further, the amplitude of the waviness increases. And eventually, at even higher velocities, we get fully turbulent flow, with the dye being dispersed across the pipe by the turbulent eddies. So here's a summary of the results of the Reynolds apparatus experiment. These are general rules of thumb, if you like, for engineering design purposes. In most cases, it's reasonable to assume laminar flow for a Reynolds number less than about 2300, but you'll find slightly different numbers in various textbooks. Some older books say that transition starts as low as 2100 or even 2000. As I'll discuss in a moment, flow transition tends to be very sensitive to the exact flow conditions. Generally, you get transitional flow from about a Reynolds number of 2300 to 4000, so a wavy type of flow that's not fully turbulent. And it's usually reasonable to assume you have fully turbulent flow for a Reynolds number greater than about 4000, although some books may specify a Reynolds number greater than 10,000 for so-called fully turbulent flow. Again, I want to emphasize that these Reynolds number ranges are only approximate. They're just general guidelines for typical flow conditions. For example, you should keep in mind that these ranges are for a smooth glass tube. It turns out that transition from laminar to turbulent flow is highly dependent upon pipe surface roughness. So, for example, if you have a rough cast iron pipe, the flow will likely go turbulent at a lower Reynolds number than in a glass tube. Flow transition is also highly sensitive to the inlet flow disturbances. If the main tank has a lot of vortices which get drawn into the pipe, this will cause the flow to transition to turbulence at a much lower Reynolds number. Conversely, if the main tank has no eddies, this can significantly delay flow transition. Osborne Reynolds allowed his tank to settle overnight and was able to get laminar flow up to a Reynolds number of as high as 14,000. Other researchers taking extreme care to avoid inlet flow disturbances have pushed this number to 20,000 for laminar flow. So I hope you can see how a Reynolds number of 2300 is just a guideline for typical flow conditions. One of the other parameters that we're interested in Lab 2 is the pressure loss along the pipe. And so you're going to be measuring the pressure loss over a length of pipe as a function of the velocity of the pipe. And here I've shown the approximate location or the approximate velocity for turbulent transition corresponding to a Reynolds number of 2300. You'll find from your Lab 2 data that in the laminar regime, the pressure loss per unit length varies linearly with velocity, whereas in the turbulent regime, especially at high Reynolds number, the pressure loss per unit length varies approximately as the average velocity squared. As you can imagine, this has significant implications for the design of piping systems. So in the laminar flow regime, if you want to double the flow rate, you have to have 2 times the pumping power because the pressure loss, to overcome the pressure loss, which varies linearly with velocity. Whereas in the turbulent regime, because the pressure loss varies as velocity squared, if you want to double the flow rate, you have to provide 4 times the pumping power. We'll discuss calculating the amount of pumping power when we get to Chapter 3. I'll end by noting that a key takeaway message of this presentation is that most real-world flows are turbulent. Laminar flows only occur when you have very small flow passages or a highly viscous fluid. And the 2 most common fluids, air and water, have quite low viscosities. So real-world flows tend to have high Reynolds number and they tend to be turbulent. And that completes this presentation.